Alright guys, we have two theorems today. We have Rolle's theorem and mean value theorem. And you can start copying this part down if you want to, but Rolle's theorem and mean value theorem are just two theorems that we're just going to have to memorize. And when we see Rolle's theorem, the key here is that the derivative is equal to 0. And if you remember one thing about Rolle, or Rolle's theorem, you want to just remember that part, the derivative is equal to 0. What it's basically saying is if we have some function that is continuous and differentiable between two x values a and b, right? That's kind of the condition. It has to be continuous and differentiable. And then the other condition is if we have a case where f of a is equal to f of b, meaning our y values are the same, then at some point the derivative has to equal 0. And remember, that's because anytime we said the derivative equals 0, we were saying what's going to happen is, not always, but our graph is essentially going to change. We'll learn what it changes. It's called concavity, but it's going to, if we have 2 points like this that are the same, at some point it did have to change direction, right? It was decreasing, and then it changed to increasing. The only time that can happen is if the derivative is equal to 0. Or there are some other cases, but in those cases it's not differentiable. So with that, an example of a graph like this, right, would be y equals x squared, or f of x equals x squared. And in that graph, right, we have lots of points where the y values are the same. So if we said on the interval from -3 to +3, right, -3, +3, we see that the y values are the same. So just on this interval here, if we just have this, then we notice our y values are the same. And you could plug those in. -3 squared is 9, 3 squared is 9. And so there has to be some point where the derivative is 0. Well, we can see from this the derivative is 0 right there. So that did work for Rolle's theorem. Now, another graph that you guys might recognize, this graph, again, at -3 and +3, this graph is equal. That's 3 and 3. And this is the graph of f of x equals absolute value of x. But there's nowhere where our derivative equals 0. So you might think it fails Rolle's theorem, but it actually doesn't, because this graph is not differentiable there. So you can't use Rolle's theorem because it has a disjoint, or not a disjointed, but it has a V shape there, so you can't take the derivative. So we're going to run through two quick examples for Rolle's theorem. The first one says find the two x-intercepts of f and apply Rolle's theorem to find all values of c such that f prime of c equals 0 at some point on the interval. Now this is a common question because if there are two x-intercepts, right, the x-intercept is where the y value equals 0. So those are 2 points where the f of a, right, would be 0 equals 0. So f of a equals f of b at those y-intercepts. So in this case, right, we want to find the x-intercepts. So where does f of x equal 0? So we'll just set the whole thing equal to 0. And I'll graph that, factor that. And we would get at x equals 0 and x equals 3. And again, if you plug those in, you're just going to get 0. So the points would be 0, 0, and 3, 0. Anyways, now we want to know if there's an f prime of c in between that. And because of Rolle's theorem, there actually has to be, but we're looking for where is that value c. So now we take the derivative, f prime of c equals, and it equals 2x minus 3. And we're going to set that equal to 0. And we'll get 2x equals 3. And then we'll get x equals 3 halves. which if you wanted to call it C, right, because it's at f prime of C, we could kind of change those all to C's. I a lot of times forget to do that step. But then with that, we know that that 3/2 is in between 0 and 3. Like if you made a number line, 0, 3, 3/2 is somewhere in between there. It's actually exactly in between there. And so Rolle's theorem worked. Another Rolle's theorem question could be to figure out if Rolle's theorem can be applied, and if it can, then to figure out, what values of C. So if you want to know if it can be applied, okay, what you would have to do, and actually one more thing, they would have to give you an interval. That's my fault. So let's say on the interval of -1 to +1. And so the first step is to test out those points. So we'd say f of -1 is equal to -1 squared minus 1 over -1. It's 1 minus 1 over -1, which is 0 over -1, or just 0. Then f of +1 is +1 squared minus 1 for 1, which is again 1 minus 1, this time over +1, but in any case it's 0. So f of A equals f of B. So in that case, we're going to try to test Rolle's theorem. We need to find where does the derivative equal 0. So just to make sure I'm using C, I'm going to change this to f of C equals C squared minus 1 over C, right? That was my original. And then I'm going to take the derivative of that. So f prime of C, this time we're going to do quotient rule. So that's going to be the top, right, low d high would be C times 2C minus high d low would be C squared minus 1 times 1 over low squared C squared. And then we would have f prime of C. Also, we don't have to do chain rule because this is f prime of C and we have C's. So C times 2C is 2C squared minus, distribute that negative sign, so minus C squared plus 1 over C squared, and that's going to give us 2C squared minus C squared is C squared plus 1 over C squared, which is equal to 0, right? We're setting the derivative equal to 0. And then we'll do the top, C squared plus 1 equals 0. C squared equals -1. If you take the square root of both sides, we'll notice that this does not exist. And one quick way to save yourself a lot of work would have been to look up at the original, right? X squared minus 1 over x. Anytime we have a denominator, if you set that denominator equal to 0, you can find out where the asymptotes are, right? So this would have a vertical asymptote at 0, which is in between that -1 and 1. So you could immediately say, you know what? This graph is not continuous, and so Rolle's theorem can't work. All right, next is the mean value theorem. And the mean value theorem says, again, same start, f has to be continuous and it has to be differentiable. And now it says there's a point where f prime of C equals f of B minus f of A over B minus A. You want to memorize this, but there is kind of a, it looks random at first. There is a meaning to this. And you'll notice, because remember, f of B is like the y value at B, and f of A is like the y value at A, and then that's right, the x at A and the x at B. So really this is saying there's an f prime of C where we have y2 minus y1 over x2 minus x1, which is slope, right? And that would be the slope between the 2 points that we were looking at, A and B. So there has to be somewhere on the curve where the slope of C is in between A and B. And what this actually looks like, just to show you guys a picture, would be if I have some curve, maybe that curve, or let's make it a little more drastic. Let's do, some curve like this. Okay, now we have A and B. And in this case, A and B can be any 2 points we want. And so here's A, here's B. And remember, we had y2 minus y1 over x2 minus x1. That's a linear. So that's the slope of the line in between A and B. So it's the slope of this line right here in between A and B. And what we call this, anytime you have a line that connects through 2 points on a curve, if you guys remember circles, a line that went through a circle, it's called a secant line. That's from geometry, but that's a secant. Just so you're aware of, the terminology, that's a secant line. And then it's saying there has to be some point in between A and B, so some point over here, C, I'll draw it in blue. So some value C where the graph has the same derivative, so f prime of C. And this that touches it in one spot where the derivative is, remember that's a tangent line. So essentially what this is saying is, if you have a secant line, somewhere in the middle of that secant line there's a tangent line with the same slope. Alright, so you don't have to know this understanding, it's nice to know that, but what you do have to memorize is the formula. So, example, find all the values of C that satisfy anytime you see MVT, that's mean value theorem, so that satisfy the mean value theorem on the specified interval f of x equals x cubed, and the interval is 0 to 1. So, in this case, first step is always basically going to be to say, okay, f prime of C is going to equal f of B, just write down your formula, minus f of A over B minus A. Then I'm going to plug in there's A, there's B. So f of B would be 1 cubed minus f of A would be 0 cubed over B minus A, 1 minus 0. That's 1 minus 0 over 1, which is equal to 1. So there is some derivative of this where it's going to equal 1. And so, again, what we can do is we could rewrite this as f of C equals C cubed, just so we remember we're solving for C. And then now we take the derivative, right? F prime of C equals 3C squared. And we set that derivative, right? We substitute that for 1. So we would say 1 equals 3 squared, divide by 3, 1/3 equals C squared. Take the square root of both sides, and we get plus or minus 1/3 is equal to C. And that's our answer. Alright, second one, f of x equals 1 over x. It's going to be the same thing, use the mean value theorem to find the c's that satisfy it. But if you're thinking ahead, okay, between -2 and 2, right, this graph is going to have an asymptote if we set the bottom equal to 0 at x equals 0. So that is in between that interval. So you automatically know that this isn't going to work. If you didn't see that though, very quickly, we could say f prime of C equals 1 over 2 minus 1 over -2 over 2 minus -2. That's 1/2 minus -1/2 is 1, right? 1/2 plus 1/2 over 4. And then we could say f prime of C is equal to, well, f of C is 1 over C, or C to the -1st. So that's going to be c to the negative second, or negative 1 over c squared. We want to know when does that equal 1/4. Well, you could cross multiply, or you can multiply by the common denominator of 4c squared, and you would get on the left negative 4 equals on the right side would get c squared. If you take the square root of both sides, that does not exist, which we already knew if we had realized that there was an asymptote there, right? Because it's not continuous. It didn't meet that requirement. Now, if the interval was different, say the interval was like positive 2 to say 6, well, now the asymptote's not in there. So you should get an answer if you did between positive 2 and 6. I'll let you guys do that on your own because this video is getting a little bit long. But anyways, have a nice night, guys, and I'll see you in class.